In this video, I want to talk a little bit about molecular orbital theory and extend it to physical characteristics of molecules and compounds. If you haven't had a chance to review a video or reading on molecular orbital theory, then you probably want to look over that first before diving into this one, because I'm going to assume a level of knowledge coming in, so we're just going to kind of get into it. Now, molecular orbital theory is all about explaining how certain elements bond together and why from an energetic standpoint, because electrons have a wave nature, and so because they act like waves, they can interfere like waves can, and if they do so constructively, then that allows for bonding. If they do so destructively, then that causes, we call it anti-bonding, but it's not energetically favorable for bonding to happen when you have destructive interference. So MO kind of gives us a way to explain why certain elements bond together, and it also gives us a way to tell you how many bonds that things will want to form by looking at the bond order. But then extending that further is we can explain some physical properties of molecules, such as magnetism, because magnetism relates to unpaired electrons. So if something has no unpaired electrons, meaning that everything is in pairs, everything that's spin up has a spin down, then it's not going to interact with a magnetic field. We say that it's diamagnetic. Whereas if I have unpaired electrons, because of the characteristic of spin, if I have an individual electron hanging out on its own, that spin is going to create its own little field, and that's going to cause it to interact with the magnetic field, making the material paramagnetic. So in past videos, I've talked a little bit about how we can do that with individual elements or with ions, and talk about the magnetism of those. And now molecular orbital theory gives us a way to talk about it in molecular, either compounds or just molecules themselves. So to illustrate that, I'm going to use oxygen, elemental oxygen, which is diatomic. So let's think about O2. Oxygen's electron configuration is 1s2, 2s2, 2p4. That accounts for all 8 electrons on a neutral atom of oxygen. If I have 2 of these and I'm putting them together, then when those orbitals interact with each other, then for the s orbitals, in alignment with the bond axis, when I'm thinking about the MOs that are going to form, the molecular orbitals that are forming, then I'll have one that is in alignment with the bond axis, so I have a sigma orbital, and then I have one that's in alignment with the bond axis, but I have destructive interference. So I have a bonding orbital and an anti-bonding orbital. Sigma and sigma star is the way that we represent that. And then the same thing is going to be true for our 2s orbital. So it's in the second shell, so it's a little bit further away from the nucleus, and so these guys can overlap, kind of a sigma, sigma star. And then my 2p's are also going to overlap. But when I think about the orientations of my p orbitals can be along the x, along the y, and along the z. And so those 3 different orientations, which we represent with 3 different orbitals, 3 different lines here, are all going to interact and intercept in different ways. So if we think about the px's, then those guys are going to interact in a sigma way, right? So the sigma here are my px's. So that interaction between these guys. And that's a sigma interaction because it's along the bond axis. So if we're visualizing what that looks like, then that's what that sigma is. But the other 2 interactions between the p orbitals are going to be in and out of the plane. So if I have 2 of my py's and they interact above and below the plane, then that's going to be a pi orbital. And then if I have pz's that are interacting kind of in front of and behind the plane of the bond, then that's going to be another pi. So these pi orbitals are slightly higher energy than the sigma, but they are still lower energy than each of the individuals on their own. So these pi orbital interactions, again, are positive. It's constructive interference. And I'm going to have the opposite on the opposite end. So these are pi's that are bonding orbitals. I have pi's that are slightly higher energy that are anti-bonding. So we call these pi stars. Now again, pi overlap happens when I have things that are outside of the plane. So above and below, parallel to the plane, in front of, behind. So those are pi's. They're not as energetically favorable as sigmas, which are in alignment with the bond axis. And so we have higher energy even though they're still bonding, and then they're kind of lower energy than the actual anti-bonding sigma orbital here, which will be up at the top. So for every bonding orbital, you have an anti-bonding orbital, and they're going to be kind of mirror reflections on either side of the orbitals that you're bringing in to overlap. So we're bringing in these orbitals to overlap. That's valence bond theory. Overlapping orbitals mean that we have a covalent bond. And then when we overlap these things, because of the wave nature of electrons, they can overlap in a positive way, energetically speaking, or a negative way, a bonding way or an anti-bonding way. So here's my MOs. Now I can start filling in the electrons that I have. Now I'll just kind of note as a side note here that usually when we're talking about MOs, we just focus on the valence electrons, the outermost electrons. I'm doing this kind of for clarity's sake. Really, these 1s's aren't going to be involved in bonding anyway, so we really wouldn't be paying much attention to these when it comes to the oxygen, but I'm just including all of them just for kind of the purposes of explaining the model. Okay, so one of the electrons from this one and one of the electrons from that one will go into this bonding orbital. And then one from each will go to this anti-bonding orbital. 2 and 2, so we've accounted for those 4. Same for this set of s orbitals. One from here, one from here. And then one up here, one up here. All right, so I have 2, 4, 6, 8, which accounts for the 2, 4, 6, 8 that I have in my S's. Now I'm going to look to the P's. I have 4 from each to work with, so I'm going to fill them in from the lowest energy up, like I do with an energy diagram in general. So 2 are going to be here, 1 from each of these. So let's just do this. Then my pi's, I can do 1 and 1, 1 and 1. So I have 2, 4, 6. I need 2 more, 1 and 1. So now I have 2, 4, 6, 8 that come from the 8 of these electrons here. Now, why did I fill these in 1 and 1? Well, that goes back to Hund's rule that electrons like to spread out in orbitals that are at the same energy levels. So for the same reason that I fill in all 3 of these first and I don't have 2 pairs of electrons here, I want to spread out as much as physically possible first before I pair up those electrons. So the same is going to be true for my molecular orbitals as it is true with the orbital diagrams that we've created when we talk about electron configurations. So now these are the MOs, and if I wanted to figure out what kind of bond is going to form, then I could calculate the bond order. So bond order is calculated by taking 1/2 the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. So again, usually you would just use the ones in the valence shell, so the outermost shell, so I'd just be focused on the 2's here, but I'll just do them all because it's going to end up being a wash anyway. So for number of electrons in bonding orbitals, I add up everything that doesn't have a star. So I have 2, 4, 6, 8, 10. 10 in bonding orbitals. Now I'm going to look for the total number of electrons in anti-bonding orbitals. So anything that has a star. 2, 4, 6. So now my bond order is going to be 1/2 of my 10 minus 6. So 10 minus 6, of course, is 4. And then I take 1/2 of that, and I end up with 2. So what is my bond order? My bond order tells me how many bonds are going to form between my oxygen. So that says there's going to be a double bond, which I would have predicted if I had just done the Lewis dot structure for it anyway, because we know an oxygen molecule looks like that and has 2 bonds, right? So this is just confirming our knowledge. But if I was to look at this and say, well, how many unpaired electrons does oxygen have? If I'm trying to figure out something about magnetism, it doesn't look like it has any unpaired electrons, right? I have, shared electrons and I have pairs on the oxygen. So I would think then that oxygen would be diamagnetic, but I would be incorrect. Oxygen, or O2, as a molecule is paramagnetic, and the reason that it's paramagnetic is because of these unpaired electrons up here in these antibonding orbitals. So again, when I look at the individuals, so if I look at just an individual oxygen atom, I might say, well, there's a couple unpaired electrons. That probably means the oxygen, one single oxygen, is paramagnetic. But when you put them together, then now these MOs give you a way to categorize the physical characteristics you would predict from the molecule, which you can't do without having this kind of schematic here that shows you how these things are going to interact, in what ways the electrons will overlap in a destructive or constructive way. So this is just another way that we can use our molecular orbital theory. I think that MOs are kind of cool and kind of fun. It's neat to be able to predict things when we start to put things together and see how that works. In a general chemistry context, it really only works for diatomic molecules, so just 2 atoms at a time. When you get more than that, it gets pretty complicated pretty quickly. So that's going to be the context that I'm kind of focusing on here. And if you have any questions, don't hesitate to reach out. Otherwise, I'll talk to you again soon.